Okay. All right, so we're gonna go over quiz number 6. Let me share a screen. Okay, can everybody see my screen?
Yeah.
Yes, no, okay, thank you. Okay, so so the question number 1 for the circuit shown, solve for the resonant frequency FR. So you apply the formula FR equals 1 divided by the quantity 2 pi times the square root of LC. Okay, so you substitute that in. So that's 1 over the quantity 1. Quantity 2 times 3.14 times the square root of 10 microhenry times 158.3 picofarad. And that should comes up to 4 megahertz. So the answer is B as in Bob for number 1. Number 2, for the circuit shown, solve for XL at resonant frequency. So XL at FR equals 2 pi FR times L1. So XL at FR is equal to 2 times 3.14 times 4 megahertz times 10 microhenry, and so XL comes up to 251.3 ohms. So the answer is A as in apple for number 2. Okay, any question number 1 or 2? Okay, no question. Next set. Okay, just get this one a little bit larger. Okay, for the circuit showing the total impedance ZT at resonant. Okay, so ZT equals the square root of the quantity Ri squared plus the quantity XL minus XC quantity square. And we know that at resonance frequency, XL and XC are equal to each other. So the XL minus XC becomes 0. So therefore, it's only leave you Ri squared. So square root of Ri squared, just the Ri. In this case, is the 5 ohms. So the answer is C as in cat for number 3. Number 4, for the circuit shown, the total current IT at resonant is, so IT equal VT divided by ZT. Okay, so and then VT, we know it's 100 millivolt divided by 5 ohms. So that comes up to 20 milliamps. So the answer is A as in apple for number 4. Okay, any question number 3 or 4?
Hi Sam, I got a question.
Yes.
How can I do that on a calculator? Because I was trying to do it, but I couldn't get it to work.
Which one? On the number 4 or number 3?
On both those. I was trying to do it, but I couldn't get the answer at all.
Okay, so number 3. So I'm just using the calculator off from the one on the computer. So we're gonna be look like so we got the quantity. So we're gonna be so if I'm looking at this one, so we got open parenthesis. So we got R squared. So in this case, R is a 5. So that's square plus, and then we got the XL over XC. We know that XL and XC are equal to each other. We don't care how much it is. It's going to be, that's going to end up canceling each other. Okay. So I'm just kind of using random number because I have to go calculate. Okay, so XL was let me see. So XL was 151.3. So I'm using 151. So let me see. So we can be looking back to calculator. So this one's going to be 151. That's for so 251. Sorry, 251, and then plus minus the 251 for XC, and that's close that parenthesis. That quantity square. Okay. And then the whole thing is going to be, and then we're going to be square. So we're going to be closing that parenthesis. And that will be the square root of that whole thing, okay? Did you follow?
Yeah, I got it. I see it.
Okay, so that's the square root of that whole thing, and we group them one at a time. Okay, so therefore it's going to be just the resistance of Ri. In this case, is the 5 ohms. Okay. All right.
Okay, thank you.
You're welcome. Okay. Okay, number 5. Okay. For the circuit shown, the phase angle between VT and IT is going to be 0 degree. Like I said, the XL minus XC, that's going to get cancel each other's out. So therefore leave you with 0 on top divided by 5. And then arctan of 0 would be yield 0 degree. You just have is the resistance. Resistant, we know the current and the voltage are in the same phase. So therefore, it's going to be 0 degree. There's no phase shift at all. Okay, so the answer is C as in cat for number 5. So number 6, for the circuit showing the Q of the coil, Q equals XL divided by RI. So Q equals XL divided by RI. We know XL was 251.3 ohms divided by RI, which is 5 ohms. And that's equal to 50.27 ohms. No, there's no unit for this one. 50.27. The closest is 50.26. So the answer is A as an apple for number 6. So any question number 5 or 6? Okay, no question. Next set. Okay, number 7, for the circuit showing the bandwidth BW equal FR divided by Q is, so bandwidth equal FR divided by Q, and then we know that was the resonant frequency was 4 megahertz. So we got 4 megahertz. That would be 4,000. That would be 4,000 kilo. That would be 4. Let me see. That's one here. It's going to be 4,000 kilohertz. Okay. And that's 4,000 kilohertz divided by 50.2726. Okay, so it comes out to 59.7, 79.58 kilohertz. So the answer is B as in Bob for number 7. Number 8, for the circuit showing the lower cutoff. Okay, so lower cutoff equal to resonant frequency minus the bandwidth divided by 2. Okay, so let me see, that would be 4,000. So 4,000 kilohertz minus the 79.58 kilohertz divided by 2. Okay, if you do that, that comes to 3,960 kilohertz. So the answer is A as an apple for number 8. Okay, any question number 7 or 8? Okay, no question. Next. Okay, what type of waveform does not change polarity with time? Okay, the only one that doesn't change polarity is your DC because it stays constant, either positive voltage or either negative voltage. It doesn't change over time. As you can see, time continues, but DC stays the same. The only one that changes is your AC, or your sine wave would change. Square wave would change. Square wave would go like this, and then comes down like this. So square wave do change, and triangle will be the same thing. Triangle will be this. Okay, so the answer is only C as in cat for number 9. Okay, number 10, for a 600 ohms load resistor connected to a generator with an open circuit voltage of 20 volt peak to peak and an output impedance of 600 volt. The generate output voltages. Okay, so you got the total of 20 volt on the open circuit. So therefore, now total together will be 20 volt peak to peak. So therefore something has to be one of them will be over 10 volt and the other one will be over 10 volt over the other resistor here. So both of these resistance are equal. So this one will be 10 here and then 10 here. So therefore it's only 10 volt that will be able to come out from the generator. So the answer is C as in cat for number 10. Okay, any question number 9 or 10? Okay, no question. Next set. Okay, for the circuit shown, the resonant frequency FR is, okay, so we apply the formula, FR equals 1 over the quantity 2 pi square root of quantity LC. Okay, so FR equals 1 divided by the quantity 2 times 3.14 times the square root of the quantity 10 millihenry times 1 microfarad. Okay, so and that comes up to 1591.55 hertz. So rounded off to 1592. So the answer is A as an apple for number 11. Number 12, for the circuit shown, the inductive reactant XL at resonance. So XL at resonance, same thing. So 2 pi times FR times L. Okay, so 2 times 3.14 times 1592 hertz times 10 millihenry. So XL comes to 100 ohms. So the answer is C as in cat for number 12. Okay, any question number 11 or 12? Okay, no question. Next set. Okay, for the circuit shown, the resistance of the coil, R coil equals XL divided by Q coil. So we got XL. XL in this case is going to be 100 ohms that we calculate earlier. XL, let me see what XL that we calculate right here. XL was 100 ohms on number 12. So divided by the 50 Q coil. So that's yield 2 ohms. So the answer is C as in cat. Number 14, for the circuit shown, the total impedance ZT at resonance is, okay, so ZT equals the square root, the quantity R plus R coil quantity square plus XL minus XE quantity square. Okay, so, let's see. Okay, so you substitute that into there. So you got the, so this one is going to be just, so that's going to be this. So like I said, XL and XC is going to cancel each other, leave you just the R plus R coil left. So R plus R coil. In this case, R is 8 ohms and R coil was 2 ohms. Okay, so therefore the total maximum is 10 ohms. So the answer is A as an apple for number 14. Okay, any question number 13 or 14?
Sam, so and that number 14, so I guess
Yeah.
that is typical to consider our coil, right? And considering Z total, I see that I for some reason I didn't include it, and my result came in at 8 ohms versus the 10 ohms that you're calculating. So I see that it should be calculated, but is it the correct thing is to in fact consider it, correct?
Yeah, you have to consider the R coil. That is part of the resistance, the R here. Okay.
Okay, thank you.
Okay, you're welcome. Okay. Any other question number 13 or 14? Okay, no question. Okay, next set. Okay, for the circuit shown, the total IT at resonance. Okay, so IT at resonance is going to be VT divided by ZT. We know that the VT is going to be 10 volt divided by ZT was 10 ohms. So that yield 1 amp. So the answer is A as an apple for 15. 16 for the circuit shown, the inductive voltage VL at resonant. Okay, so VL equals IT times XL. Okay, so we know that XL is 1 amp times the XL, which was 100 ohms that we calculated earlier. Right up here, number in the question number 12. Okay, so times 100, so 1 amps times 100 ohms, that's yield 100 volt peak to peak. So the answer is C as in cat for 16. Okay, in the question number 15 or 16. Okay, no question, next set. Okay. Okay, at resonant, a series RCL circuit acts as, okay, so Z, so we're going to be, like I said, XC going to be cancel XL going to be XL and XC are equal to each other. So XL is going to be subtract XC, so that would go to 0. So this is 0 here. Leave you with the R square. So square root of R squared, just leave you with the R left. So R is the resistant. So resistant doesn't, so the current and the voltage does not are in phase or has 0 degree phase shift. So the answer is C as in cat for 17. Number 18, the impedance in the series RCL circuit resonant. Okay, is okay. So it's going to be minimum. Like I said, XL and XC gets cancel each other, leaving you R squared. So square root of R squared, just leave you R total. In this case, it's going to be just a minimum resistance. So you're going to be, the resistance is very, very small. So the answer is C as in cat for number 18. Okay, in question number 17 or 18.
Would you go over 5 and 6 again, please?
Okay, 5 and 6. Okay, so question number 5. Okay, like I said, okay, so question 5 is going to be, like I said, when you calculate, so it's going to be your phase angle is going to be arctan of the quantity XL minus XE quantity divided by RI. So RI is in 5 ohms. Okay, we know that XL and XC is equal to each other. So in this case, XL was 251.3 ohms. So therefore, this one substitute 251.2.3 and 200, and then XC would also 251.3. So this minus this would become 0. Okay. So the RI is just the 5 ohms. So 0 divided by 5 will be 0. Arctan of 0 is going to be 0 degree. So there's no phase shift. So the current, and the voltage would be at 0 degree. There's no phase shift. Okay. So the answer is C as in cat for number 5. Okay, number 6, for the circuit shown, the Q of the coil, Q equals XL divided by RI. So XL was 251.3 ohms divided by RI was 5 ohms. So that yield 50.27, okay, or 26. So the answer is A as an apple for number 6. Okay.
Thank you.
You're welcome. So
Yes.
any other question?
Yeah, can I see the question 17 and 18 only? I just want to see the questions.
17 and 18, okay. Circuit at resonant, no, so at resonant.
Thank you.
You're welcome.
A quick question. Maybe Mr. Pham would be able to clarify the conditions of Q for the coil efficiency. Would it be more of in understanding the coil, it's burn-in time, or it's a matter of how the coil is made, to where if it's burnt, actually electrically, fried, as in melted, as in if the coil is used specifically within the circuit, that the coil literally gets overheated, determines the Q of the coil, or is it the wrap, the metal wrap of the wire around in a coil that defines what a coil is, or is it the actual material that is defining the Q of the coil? What is the actual conditions of a coil other than the math and the components? What is actually damaging the Q of the coil as far as its usage in a circuit?
Okay, basically, you have to deal with the circuitry working. We're not trying to do with something wrong with the circuitry. The formula only applies for the circuitry working. Something wrong with the inductor, then you can not talking about the Q, anything.
Hey,
Let's see who else. Okay. All right. Any other question? Okay, back to you, Mr. Pham. Thank you.
Thank you, Sam.
You're welcome.
Okay, so today I can get the first lecture for the transformer. And the next will be, I will be have the student working on the lab on AC1. The thing is, get this program are very, very hard to run. The reason is the level is not the same. Some students, they already know something, they can get everything done quick. That's okay. That'd be fine to me. You can take easy. However, for students never doing anything in electronic. So that's why we have to make sure they know what they are doing. That's why I have to spend time to help them in order to do for the level. Level is a very good system for training. Okay, let me see, I can convert it into my iPad. Okay, so now we're talking about the transformer. So basically, to get a transformer and the next time will be power in the AC. That basically is not important. Okay, and also I already upload the RF introduction. You need to download that to read it. Okay, in order when we're talking about, you're able to understand. Okay, this is a symbol for the transformer. Suppose two inductor are placed in a closed proximity to one another, but no electrical connection exists between them. Okay, and suppose also that an AC voltage is applied to one of the inductor. Okay, that means you apply the voltage. Okay, the magnetic field surrounding the inductor with applied voltage into voltage into the other. This phenomenon is known as mutual inductance. Inductor coil arranged in this manner result in a common electrical device called a transformer. That's just given to you. How they can get the transformer. Okay, basically this you can read it again when you do your left volt. That's coming out from the left volt. The coil or winding with the applied voltage is what we call a primary. Okay, so this part we call a primary. This one they call a secondary. The amount of voltage induced in a secondary depend on ratio of turn of Y between two winding. Okay, that means how many turn of Y for the first, how many turn of Y for the second. Okay, in the figure, which coil or winding is the primary? That's a very simple. Okay, if you follow it, you are reading, you understand, then you know this is a primary. This is a secondary. Okay, so basically, applied voltage will be a primary. Induced is a secondary. Okay, on this one they just turn around. And the answer will be primary L1 or L2. L1 or L2, quickly.
L1.
L2.
L2. You understand, we already said, when you apply the voltage, then that means the primary. Induced, secondary, right here. Primary. And that induced, secondary. Okay?
Hey, Mr. Pham, quick question.
Yeah,
So basically, when we're looking at primary is the source of the voltage or whatever, correct?
correct.
Source. Okay, thank you.
Okay, and different type. Iron core, ferrite core, air core. That means the symbol for the transformer. Okay. Above are various transformer schematic symbol. The present or absent applied between the coil indicate the type of the core being used. Just a symbol. This configure so iron core transformer with a tap secondary. Okay, you can see this is the one here, the tap. That means they divide secondary into two parts, one from here to here, and one from here to here. That's what they call a center tap transformer. This tap may be used to help the turn ratio between two coils. Okay, now the turn ratio of the transformer is the ratio between the number of turns of wire. On the primary, they call MP, and the number of turns of wire secondary and F. So 10, okay, 1. 10 for primary, and 1 will be for secondary. Okay. A transformer with 1,000 turns on the primary, 100 turns on the secondary has a turn ratio of 10 to 1. That means NP divide to NS, you can get 1000 divide 100. So you get a 10 and 1. The ratio between the voltage on the primary VP, voltage on the primary, and the voltage on the secondary, we call a VF. Primary voltage, secondary voltage, equal the turn ratio of the transformer. So basically, you get NP over NS equal VP over VF. That's the formula will be helping you to do calculation. And now, for example, if there were 10 volts at the primary with a turn ratio 10 to 1, then there would be a 1 volt at the secondary. Okay, that will be helping you if you want to calculate the VF. Then VF will be equal NF times VP divided to NP. You get a 1 volt. The transformer having a secondary voltage that is less than the primary voltage. That's what we call a step-down transformer. What that means? When you get a 90 volt at the primary, go through transformer, you get 30 volt. Okay? VS less than VP. That's what they call a step-down. Okay? Transformer. However, if you get a VP 30 volt and VS 90 volt, that means the secondary higher than the primary, then they will be get step up transformer. Okay, that's what we call step up transformer. So now you're able to identify based on the voltage of the primary and the voltage of the secondary, and you know they will be a step down transformer or step up transformer.
Mr. Pham, quick question.
Yeah.
Typically, most of the time we see step down, that is from primary to secondary. But what are the situations where you're using step up? Because usually on the primary side, that's where the source or like the generator or whatever it's coming from. So how does that work with the step up?
Normally, okay, you can see most of time will be a step down.
Correct, correct.
However, how come you see they need a step up transformer? Okay, you didn't see much on the step up transformer, but I can tell you one thing. You can see the new car, they get 110 volt AC, right?
Right.
So in order to get 120, they have to get a step up transformer.
Mhm.
Okay, the thing is in the car, okay, you cannot get a higher voltage to going down. You can get a small voltage and you want up to like the power at your house. So that's why they have to get a step up transformer.
The reason why I was asking, because typically on the primary side, that's the source side. And on the secondary, usually it gets its energy or voltage from the primary side. So where does the secondary get that extra voltage or whatever to step up the primary, which is a source? That's what the confusion is.
No, that's the only thing is you can get a small voltage on this primary. Then now they have to design so they can go up to 110. That's using in the car. Otherwise, no way you can get 110 volt AC in the new car.
Okay,
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 the tap upper center tap winding divide the number of turn in half. That's what they try to explain to you. Like I already talked to you. Okay, you get 1,000 turn in the primary. Normally, if they equal, you can get 1,000 turn here. Okay, and now they want to divide. Okay, if you get a 500 turn at the output here, secondary, then they get a tap in here. They will be get a 250 up here and 250 going down here. Total will be a 500. And also you have to understand the signal from number 3 to number 5 or number 4 to number 5. They equal the value. However, all the time they have to be opposite, okay? 180 degrees of phase. That's what they need to center tap. Apply 12 volts sideways to primary right here. Okay. Of this step down transformer result in 6 volt. That means from 3 to 4, you get a 6 volt. Okay. If you measure across the entire length of the secondary, okay, 3 to 4, and in 3 volt, 4 to 1. Okay, if you measure from center tap to one end, basically they just telling you if you measure from number 3 to number 5, you get a half 6 volt. Okay, and another 3 volt here. Only thing that they could be opposite. So this is the whole secondary voltage. However, if you measure from 3 to 5 or 4 to 5, you will be get a half of that voltage.
Does the gauge of wire determine how many wraps or turns?
Now, data depending on the tone right here. You see how 1,000 tone, okay? And if you connect this way, they get a 500 tone. So they could be a half of 500, a half of 500.
But the gauge of the wire for making the turns has to be the same for both sides, correct? Or can the gauge of the wire be different?
No, I think the same. Why different?
Well, one's going to be a thicker material and less current versus a.
They're supposed to be identical.
Right, that's what I'm clarifying. Thank you.
The current ratio between the primary current IP. IP means primary current and IF will be a secondary current. Okay. Current ratio, that means to take a IF divide to IP. The current ratio is the inverse of the voltage and the turn ratio. That is, if the voltage ratio increase, then the current ratio decrease. If the voltage ratio decrease, current ratio will be increase. That means they revert. Okay. A transformer with the voltage and the turn ratio 10 to 1. At the secondary current, I secondary 100 milliamp. What is the primary IP current? So NP over NS equal IS over IP. If now they want to calculate the IP, IP will be equal NS times IS divided Q, and P. If you do it, then you can come up with A or B or C. I'm not doing calculation. Okay. But when you're working on a lab phone, you have to select either A or B or C. If the load IL across the secondary of a transformer change, they can be increase or decrease. The transformer automatically increase or decrease the primary current. This characteristic of automatic compensation, why AY transformer is a self-regulating device. That means if you change the load, that means you change the current, okay? And transformer will be adjust that current. The power in the primary, P power of primary equal IP times the voltage applied equal the power in the secondary, PS equal IF times VR load in ideal transformer. In practical transformer, however, primary power in can equal the secondary power out only when the transformer is 100% efficient, which only occur in an ideal transformer. That means that condition never happen. After you measure the primary and the secondary power, you can calculate the efficiency of the transformer from the following. Okay, how efficiency percent? You can take a P power of the secondary divide to power of the primary times 100, telling you how many percent of the efficiency. An ideal step down transformer with a voltage ratio 10 to 1. At the input power, P primary 500 milliwatt. What is the power out? P of the secondary. Okay. Let's see. You can get the formula. Okay. Let's see. P, where the formula? They supposed to be equal, but they're not. You can get that one will be primary 500 milliwatt, and they want to know what the PF equal. So what I said, when you go working on the lab board, you have to select either A or B or C. Okay. Now this is the one we want to emphasize. Now you're looking up for the circuitry here. That's a generator, internal resistance 50 ohm. And the load will be 25 ohm. Okay. So if you want to calculate the power at the load will be V source divide RI plus R square divide time RL. That means V divide to R I plus R square times RL. Okay, now for the first one, A here, calculate telling me what you get for the power at the load. Okay, anyway, they already calculate for you here. For this circuitry here, power at the load 444.4 milliwatt. Okay, basically you can take the output V square divided to R. On the second one here, you get this the 50 ohm, this the 50 ohm, and you get the power at the load 500 milliwatt. And the next one here, you can get 50 ohm, 75 ohm at the load. You get 480 milliwatt. So that will be telling you what story for this.
Mr. Pham,
Yeah,
so by showing A, B, and C, and obviously the thing talks about transformer used for impedance matching. So the one where the RI is 50 ohms and the RL is 50 ohms, that's where you have the impedance match, right?
right,
And then, and the A and the C are not impedance match.
exactly. That's only telling you one thing. R load 25 ohm, less than 50 ohm on the second one. And the third one, RL 75 ohm, greater than 50 ohm on the second one. Both the power still less than 50 ohm. The thing you need to understand is you get the maximum power. Then you want the impedance, the load in here, internal, and the loads outside, they must be matching. Okay, 50 ohm the same, 50 ohm. Then you're able to get a maximum power. If they're not matching, not the same, then the power will be less.
Now that has an effect with speakers, right?
Yeah.
Okay, thank you.
Now, they can using transformer to make the matching for the impedance. If you're looking on this circuitry here, you get a load 4 ohm. However, internal of generator 50 ohm, they cannot match it. So that's why the power at the load here cannot be maximum. We'll see what happened. A transformer can make a load IL resistance appear to the primary at the value larger or smaller than its actual resistance value. That means the transformer will be half. So for the circuitry, look like the load is not 4 ohm, and they will try to matching 50 ohm on the generator. Okay, suppose it is necessary to transfer 500 milliwatt of power to 4 ohm. Okay, they try to get the 500 milliwatt to 4 ohm. To transfer maximum power from generator to the load must somehow to be transformed to a value equalizing 50 ohm. This we can use transformer to step up the 4 ohm load in the secondary to 50 ohm. That means they try to, using the transformer, try to make sure you can get a 50 ohm load. Okay, the impedance reflect back into the primary of the transformer. They're using the following equation: G impedance, okay, equal NP over NS square times GS. GS means secondary impedance. Okay, and you can see the calculate GP equal 3.53. Okay, divide to 1. Okay, time 4. That's what you get, 40 ohm. 3.53, that's the primary body. Second will be 1. Okay, and that they telling you, okay, primary of the impedance instead that guy. Now they try to get in here, 50 ohm. Okay, and PL will be VS square divide RL. Okay, VS square is 1.14. Okay, square divide to 4 ohm. So that's why you can get a 500 milliwatt. Now, do you know how come you get VS 1.41 volt? I believe if you get a 10 volt here, a ratio will be 3.53 to 1. So you're using the formula to calculate the VS. So that's why you can get a VS equal 1.414. Okay. And now you take the power in the load. You take that voltage square divide to 4 ohm. That's why you can get the 500 milliwatt. So basically, they're using the transformer here, try to calculate, make sure that load in here, basically through the transformer, they can get a 50 ohm. You can see you get a 50 ohm here, and now they get a transformer, primary of the transformer will be 50 ohm. So voltage here will be a voltage divider. Okay, so that is they using the transformer. Okay, try to have in order to get the maximum power at the load. And this one will be helping you calculating the required turn. That means how do we calculate this turn in here? That's what they given to you. Train to transform 8 ohm resistive load in the secondary, 1 kilo ohm in the primary. Calculate the required turn ratio, NP over NS. So NP over NS square of the GP over GS. They will be square root of 1 K ohm. That means NP. Okay. And 8 ohm. That will be for NS. So you can get the ratio will be 11.8 divided to 1. 11.8 to 1. So basically, designer, engineer, they have to know in order they can design the circuit they want. But we not design anything. Okay. And the last one here, for the circuit show, calculate the primary impedance GP. We already given you the formula. GP equal NP over NS squared times RL. If you substitute NP 5 and NS 1, 5 divide 1 square is 25 times 8. Okay, so you know what you get. And the last one, calculating the required turn ratio. That means the required turn ratio here. To find the turn ratio NP over NS when the impedance ratio is known. Then you can get NP over NS equals square root of GP over GS. Example. It is designed to transform 8 ohm resistive load in the secondary to 1 kilo ohm in the primary. Calculate the required turn ratio NP over NS. So basically for the transformer, very simple, okay? That means only thing is the last part here for most likely engineering, okay? They have to go into the detail. Only thing is, what I want you're looking into the circuitry, you know this is a transformer. If they given you the ratio, okay, and they given you the primary voltage, you're able to calculate the secondary voltage. If the primary voltage higher than the secondary voltage, that will be step down transformer. If the primary voltage less than secondary, that will be step up transformer. Okay. Basically, not much thing happen here. And also make sure the thing I did one you will be learned again in electronics. Okay. Now, center tap transformer. Okay, you can see this a primary. However, in the secondary, they divide it in the middle here. In both part, get the same value. For example, if you get 1,000 turn from 3 to 4, they supposed to be 500 turn. And if you measure from 3 to 5, you get 250. 4 to 5, you get 250. They equal. Only very important thing, make sure you understand the signal on the 3 to 5 and the signal 4 to 5. Only thing, they will be opposite. Okay? If the first one going up, then the second one will be going down. Okay, so any question for the transformer? Okay, if it's not, so I have to stop this guy, okay? And we go into the lab. If you already know how to do what to do, AC, I believe some students already get it done, but most of them it's not. So I try to help, okay? Now I need to share. Okay, let me turn on everything. Okay, first thing, we're talking about that one here. Okay. Now I need to get picture here. Okay, so first thing, you can looking into generator and oscilloscope again. I want to make sure you understand in this one. I only talking about oscilloscope we're using in the lab. Try to get along with that oscilloscope and the generator. Okay. So before you want to do anything with the scope, then I said yes. First thing, you can set the each window. What channel you want? Channel 1 or channel 2. Okay. So in I set channel 1, and say next one channel 2 and channel 2. That is the first thing. Second thing, what we want to measure on channel 1. I want to measure the peak to peak. Channel 1, I want to measure the frequency. Okay. And same thing for channel 2. That is basically we work. And now we're talking about generator. And the generator here, you can see first one is the range of the frequency 10, 100, 1K, 10K, 100K. Okay, 1 mega. So basically, depending on what frequency you apply, you set the range. For example, I want a signal with 100 Hertz. then you can put a drain in a 100 or 1 kilohertz. That'd be fine. But they said, okay, I want the signal at a frequency 4 kilohertz. Then now you're looking, if you set a 1 kilohertz, you cannot get up to 4 kilohertz. You have to set the range to 10 kilohertz. Now you understand. That is the first thing you have to make sure you get the right answer. And next one, they can want to get a signal, okay? That means you want sideways, you can set to the sideways or triangle way, okay? Or square way. You see that? Triangle way or square way, okay? We want sideways. And this is the amplitude here. You can amplitude to make it bigger or smaller. Okay. So now I go to the amplitude to the minimum. Okay. That means counterclockwise to 0. If I reading on the free voltage, they say basically very small, around 1.4 or 2 volt. That means when you turn the amplitude to the minimum counterclockwise, you get a voltage around 1.5 volt or 2 volt. That means that is the one generator can give it to you. However, if they say I want a sideways 300 millivolt, what can you do? People know how to do it, just let me know. The thing is your generator only given to you around 2 volt maximum. Cannot be less than 2 volt. However, the required they want 300 millivolt or 500 millivolt. How can we get that voltage smaller? If you're using generator. Okay, you have to answer me. You have to let me know. Or you say you don't know.
Can you reduce the amplitude?
Yeah, you turn the amplitude to the minimum, counterclockwise to the end. And the voltage they given you only 1.5 volt or 2 volt. Now I say I want output to be 300 millivolt or 500 millivolt. Then what can we do to get that voltage?
Use the attenuator.
Using what?
Attenuator.
Where? How? I understand you're talking about attenuator. Let me divide it. You assume on the voltage. However, right now we're on the generator.
Pull the amplitude knob.
How can we get up to 300 or 500 millivolt from a generator?
Pull the amplitude knob out.
Okay, that is what he said. You see the knot with the minus 20 dB. That's what we're using. Okay. You pull it out here. Okay. Then now you can get the generator. You can scan here. They can give you a generator. Let's see. I make sure my channel 1 will be by 1. Okay. And I press channel 1. Okay, I have to scan 2 by 1. Okay, auto set measure. Okay, so now you can get 176 millivolt. You see that? Make sure in the generator they get they show you minus 20 dB when you pull it out. Pull it out. Okay, so you can get a smaller voltage. So make sure you will be hitting to that. If you want more, go to 20 millivolt. Then the level, when they did it, they already designed in the level circuit board. They get what they call a attenuator. You can connect the generator to input of the attenuator, and the output will be connected to the circuit. Then you're able to get up to 20 millivolt, okay, or 30 millivolt. Okay, so that is the one. Now you can, any question regarding into the generator and the oscilloscope. Okay, no question, right? Now, we want to do this one. Okay. What they want to connect this circuitry. Okay. On the DC-AC waveform circuit. This is a circuit they want to make a connection. So now you can see the circuitry here. Okay, you can see this circuitry here. This is a generator. This is a DC voltage variable. And they want generator go to R1. Okay, and you understand when you see dot and dot and dot, that means a broken line. So if you want to connect that to the circuit you want, then you need the two pole connect here. Okay, so that will be make the circuitry you want it. If you get a wrong connection, they're not working. Okay, and now what they said, here terminal port connect the circuitry. Okay, here the two port connect. Okay, and next one, turn on generator and set frequency to 60 Hz. So that's why they want a 60 hertz. So basically the frequency range, you can put it into 100. Okay, for example. Okay, and auto major. Okay, and you want the frequency to 60, let's see how many, 60 hertz. Okay, 60 hertz. And now you're looking into your generator and the oscilloscope. Right now they show on the scope a 30 to 38 millivolt.
Can you focus?
Okay? I want 6 volt. Everything you changing. You must set auto set measure. That's the scope measure for you. Right now, I get 300 millivolt. So you want 6 volt, increase your generator. Okay. When you increase, press auto set measure to see what the scope measure. Okay, right now, 6.8 volt. You want to go a little down. Okay, that's close. If you're looking on the display, how many cycles? Let's see. 1, 2, 3, 4, 5, 6. I don't want too many. Okay, I want 2. That's good enough. In order to do it, you can change the knot here, second per division. See that? Look at much better. Okay. And now, when you're reading here, they're telling you channel 1 vertical coupling AC. That means you have to set the channel 1 to AC coupling. And channel 1, a 28 0.1 volt per division. You don't care about that thing. That is the own oscilloscope. They don't have a automatic like this scope. But like they say, set horizontal time, be control 2 milliseconds per division. That doesn't matter for now. Only thing what they want 60 hertz, 6 volt peak to peak. Okay. If on the display here, you get 60 hertz and 6 volt peak to peak, that be fine. You understand the left one, they using their own oscilloscope, so that's why they can set this one. After you get along with the new scope here, this is not a problem. Okay. Okay, they say connect channel 1/10 probe, okay, across R1 like they want it, okay. So basically, this is a generator. And you want to connect the generator. Okay, let's connect to generator here. Okay, and also we need the route for the generator. So that will be the route. Generator route. So you connect the generator here into generator. Okay, and the route will be go to the route. Okay. Only thing is you can using by 10 probe, but normally I using by 1. Okay, I don't have to follow it. If you understand, by 1 of your scope probe matching with by 1 in the oscilloscope for channel 1, that be 5. Okay, and they want to see what the value peak to peak, and they divide by 2, you get the V peak to enter. That's okay, no big deal. Okay. And now they said they want to using the meter to measure the voltage. That's easy. Okay. You can connect the meter, make sure they measure VAC. The meter cannot get any volt peak or peak to peak. Only thing they have to get a VIMF or VAC. So when you measure whatever value you get, you enter. Now, let's say some circuit equipped with current sensing R2. You can see on this circuitry here. You see the port here. across R2 10 ohm. That means look like no R2 in the circuitry. If you get the connection here, bypass R2. Why they get this one? The reason is they want to measure the current in the circuit. Okay, but the way the connection here, you cannot be breaking the circuit wire to measure the current. So that's why they adding the 10 ohm. Later on, they telling you to measure the voltage across the 10 R2 10 ohm. If you get that voltage, you divide to the resistor, then you get the current. Okay, not direct measurement the current, but they want to measure the voltage across 10 ohm, then you divide. Okay, let's see. This is just an explanation, like I already telling you. See that? They measure the voltage across R2, connect the scope, okay? Then I will be voltage divide 10 ohm. Then you get a current. Okay? And here, they just do calculation. You can read it, you can enter, you can get the value. I just show you what to do. Okay? And also on that one, let's see. I try to see I can do for you on that one. Ten ohm resistor R2 at the current sensing. If the voltage across R2 is 50 millivolt, what is the circuit current? That's the easy one. Okay, I want to do. Okay, when I get into the one they telling you, and also in here, this circuitry, they want to know how to measure the voltage VL1. When you want to measure the VL1, only thing, if you're using the meter, you can connect high side here, low side here. However, using oscilloscope, you cannot. So that's why you have to connect channel 1 in the top and scope channel 2 in the second. Okay? And the VL1 will be the difference between scope on the top and the second. In the own oscilloscope, they're telling you, in order to prevent L2, we don't care that be one, whatever they said. But they tell you they need the add inverter to measure. That means you measure channel 1, you measure channel 2. I given you example. This be B. So VL1 will be VA minus VB. The on oscilloscope, they don't have a minus. They get a function they call add. Okay? So in order to add 1 to 2 to get a difference, then they telling you, I need to revert channel 2. That's what they call invert. Okay? Channel 2, then you can add it. On this scope, we don't have to. You can using channel 1 minus channel 2 to do it. Okay, let's see. Now, locate the inductive reactant. What they want? They want 10 volt peak to peak and 1 kilohertz. Okay, what I telling you? First thing you want to do, you have to make sure you make a right connection for the circuitry first. Okay, let's see. Okay, so now you can see this is the circuitry. You want to connect it. Okay. So the first thing, if you're looking on the circuitry schematic, they want it generator will be connected to R1. Generator here connect to R1. So you have to make this connection first. Okay. Then circuitry will be go to L1, L2. Okay. L1, L2. So basically L1 here, L2, L3, okay, and so on. So you want to connect it to connect to L1, L2. You need to connect this one. Okay, and the generator will be connected here. And the route will be connected to the route. Okay, that's what they want. And now you can see what the voltage and frequency. They want 10 volt. So you, right now we get 6 volt peak to peak. You can increase the frequency of amplitude to get to 10 volt. Okay, that's close to 10 volt. And the frequency now will be a 1 kilohertz. Okay. Then you can connect that auto set measure to see what the frequency right now. Okay. Frequency just about 60 hertz. So you change the scale, the range of generator to 1K. Okay. Press auto set measure. Right now, frequency you get 610. You have to change the frequency to 1K. Okay, auto set measure. Okay, so you get a 10 volt and frequency 1K. See what else they want you to do. Now, use the scope to measure the peak voltage across R2. So now you connect channel 1. Okay. Remove that port if you not connect. Okay, let's see. Channel 1. You can connect either channel 1, channel 2, doesn't matter. Okay. Okay, you connect then one in across R2. Let's see, auto set measure. You can see the signal look like too much noisy. Okay. I want to make sure everything connects. Okay. So this go generator coming out here, go to L1, L2, and now we want to measure the voltage across R2. Okay, anyway, you can see they get a lot of noise. Now, if you want to measure the V peak to peak, what can we do? If you're looking, okay, when you get the noise here, too much noise, then what you have to do after using the cursor, okay, to measure the top and the valley of the signal and get the delta difference. Okay, so anyone will be working on that. Tomorrow, I will be in the lab, so you get a problem. I will be help you out. Okay, and also I want to bring up that one. Okay, and now they want to measure the voltage across R1. Okay, channel 1 connect to the left side R1, channel 2 connect to the right side. Basically, you have to using the function channel 1 minus channel 2. So you can open this is a help for you. You want to measure for the signal unrounded voltage, you enter number 7. They're telling you, set both channels at the same voltage. Okay, that means channel 1, channel 2 must be set it to the same voltage. Second thing, you press the math function. Then you press the channel 1 minus channel 2. Number 4, press cursor button. In the type window, select voltage. In the short window, select math function. Move the cursor to measure math voltage. Read that data in the delta window. Okay, that will be helping you how to measure voltage across R1 in this case, or L1 also the same way. Okay, so up to this point, you get any question, anything? The thing I just go through the circuit, make sure you connect the right circuitry on the level circuit board to the one they want. And I just bring it up some special measurement and you don't know. Like later on, you can see measure the phase angle. And I will be teach you how to do it. Okay, up until this point, any question? No? Okay, so if not, then we'll be good night, everyone. Good night.
Good night, Mr. Pham.